Hi, I'm Bob. Welcome back to 5 Minute Econometrics, a program dedicated to fundamental econometric concepts, estimation methods, and identification strategies. We have learned Gauss-Markov Theorem. It consists of 5 assumptions: linear in parameters, random sampling, no perfect collinearity, zero conditional mean or zero correlation, and homoskedasticity. Homoskedasticity is the fifth Gauss-Markov assumption, which states that the variance of the unobserved error term is constant. In mathematical terms, the variance of the error term, denoted as mu, conditional on the explanatory variables x, equals sigma squared, where sigma squared is a constant that does not vary with x. When this assumption is violated, we say that the model suffers from heteroskedasticity. In this case, the variance of the error term mu, conditional on the x, is represented as sigma I squared. The subscript I on sigma squared indicates that the variance of the error term depends on the specific value of xi. In other words, the error variance changes with x when heteroskedasticity is present. One example of heteroskedasticity can be found in the hourly wage equation, where educational attainment is used to explain hourly wages. Heteroskedasticity occurs when the variance of the unobserved factors in the error term increases with the explanatory variable, which in this case is education. Residuals, the estimate of the error term, can help us visualize the pattern of the error variance. We can plot the residuals against the explanatory variable to observe any trends. After regressing hourly wages on years of schooling, we store the residuals mu hat using Stata's predict command with the residuals option. Then we use the scatter command to visualize the distribution of the residuals. As individuals attain more years of education, we notice that the residuals become more widely distributed. For individuals with more years of education, their residuals fluctuate more widely than those with fewer years of schooling. It is evidence of an unconstant variance of the error term. The error variance increases with years of education. In other words, the error term demonstrates heteroskedasticity. First, heteroskedasticity does not cause bias or inconsistency in the OLS estimators of the coefficient beta. When the first 4 Gauss-Markov assumptions hold, the OLS estimates are unbiased and consistent. The key assumption for unbiasedness in finite samples is the zero conditional mean assumption, and the key assumption for consistency in large samples is the zero correlation assumption. It has nothing to do with the structure of the variance of the error term. Second, the goodness of fit measure R squared is not affected by heteroskedasticity. By its definition, r squared equals the explained sum of squares divided by the total sum of squares, or 1 minus the ratio of the residual sum of squares to the total sum of squares. The three sums of squares are unaffected by heteroskedasticity. The same is true when we use degrees of freedom adjustments to compute the adjusted r squared. Third, the OLS estimates may not be efficient in the presence of heteroskedasticity. That is, the OLS estimator may not have the smallest variance among all linear and unbiased estimators if the error term is heteroskedastic. For instance, if the variance of the error term is a linear function of the explanatory variable, the weighted least squares WLS estimator may have a smaller variance than the ordinary least squares OLS estimator. Only when the error term has a constant variance, along with the other four Gauss-Markov assumptions, linear in parameters, random sampling, no perfect collinearity, and zero conditional mean, the OLS estimators have the smallest variance among all linear unbiased estimators. The OLS estimator is called the best linear unbiased estimator, blue, under these five Gauss-Markov assumptions. When heteroskedasticity is present, OLS estimates may not have the smallest variance among all linear and unbiased estimates. Fourth, the statistical inference may be misleading if the error term is heteroskedastic. The variance of beta hat is based on homoskedasticity. It will be biased without the homoskedasticity assumption. As a consequence, the standard error of beta hat will no longer be valid for constructing confidence intervals and t-statistics. The usual t-statistic does not have the t-distribution. It leads to an invalid t-test. Similarly, f-statistics are no longer f-distributed, and the LM statistic no longer has an asymptotic chi-squared distribution. The statistics we used to test hypotheses under the Gauss-Markov assumptions are not valid in the presence of heteroskedasticity. When the variance of the error term is not constant but varies with the explanatory variable, the model suffers from heteroskedasticity. It plays no role in the unbiasedness or consistency of the OLS estimators. However, in the presence of heteroskedasticity, the OLS estimator may not have the smallest variance among all the linear and unbiased estimators. The statistical inference procedures based on the T and F distributions may no longer be appropriate either. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.